This is going to be a quick video about where do these, the ideal gas law, where does that come from? Previously, we've seen that pressure and volume, for example, are inversely proportional. So it'll look something like this. Because when I multiply pressure times volume, I always get some constant, some number. And we saw the same thing was true when I had like pressure and temperature. Looks something like this, where P over T equals, again, some number. If I keep doing that and I repeat that process with all of these different variables, pressure times volume was constant, over temperature, also constant, over the number of moles, also constant, so that all equals some number. We call that number the gas constant. Depending on whatever these units are, we get a different number for this gas constant, just depending on how much these measure in terms of pressure and volume and temperature and the number of moles. So for example, if I take the pressure in, we could do like ATM, or we could do millimeters of mercury, or we could do in kPa. Volume is almost always in liters. Temperature has to be in absolute, so it's going to be Kelvin or some other unit called Rankine. We won't use that. Or, and then N has to be the number of moles. So if I take those and plug in some of those units, our gas constant is going to look like maybe ATM times liters divided by Kelvin times moles. Could be some number like that. That is going to be the most common gas constant that we see. The ATM liters, Kelvin moles. Another very common one, because ATM is one that makes a lot of sense. There's one ATM as the standard pressure. kPa is also extremely common because that is the SI unit for pressure. So we could also see this as kPa times liters divided by moles times Kelvin. Doesn't matter what order, but usually you'll see it in this order, not this one, whatever. And then the numbers that go with these just come from plugging these in for an ideal gas. And we'll talk about that, what that means in a second. So this is 0.0821, and this is 8.314. You do not need to have these numbers memorized. You'll be given these. These are stupid numbers to have to memorize. What we do need to know is how to use these units. So when I pick this gas constant in the ideal gas equation, which I'll talk about in a second, then we have to pick the one that has the matching units. The other thing I want to mention in this video is I keep saying this term ideal gas, because gases, well, they don't behave ideally. Gases in our simulation on PhET, we pretended that they were perfect little spheres. When they collide, they perfectly bounce off of each other and go in different directions. So we pretended that they have no attraction to each other due to their intermolecular forces, which depend on the size of the molecules. We also pretended that the particles themselves don't take up volume in our volume, that the volume only comes from the collision of the particles against the sides of the container. Neither of those things are true in real life, but we can assume it for most cases. So an ideal gas is a gas where we assume that there is no attractive or repulsive forces. Assume no, I can just say IMFs, right? While a real gas, it does have IMFs and the particles do take up space. We will not look at the formulas for real gases because they take a little bit more algebra and a little bit more time to work with. So you'll see those if you go on to AP or IB chemistry, but you won't see them here. So in our notes, an ideal gas is assumed to have particles who exhibit no forces, and a real gas does have IMFs, particle volume, and it can also change states. So we had this idealized version of these graphs, right? That's really only true for particular pressure and temperature. If I were to take this graph and zoom out, it might look a little bit more like this. Here's pressure, here's temperature. That linear part might be this teeny little section where the pressure and temperature are in a realistic range. But when I go to these extremes, it might look a little bit more like this. So our little section we looked at, yeah, it was linear enough that we can use an equation. But when I get to these crazy parts, it no longer follows these gas laws, because at a certain temperature, it's gonna freeze, and at a certain temperature, it's gonna turn into a plasma. So this is really only true when we are at relatively high temperatures, we still have gases, and we have relatively low pressures. If the pressure increases too much, we're gonna force our gas to become a liquid and then a solid. For ATM atmospheres, this constant is 8.314. And for kPa, this is 0.0821.